Welcome to Circuit Masterclass, your go-to channel for everything in power systems, transmission, and distribution engineering. Don't forget to check out circuitmasterclass.com for in-depth blogs and bonus content. We have provided the website link below in the description. Let's get started. Let us have a discussion on the minimum oil circuit breaker. Before discussing the minimum oil circuit breaker, let us recall our knowledge regarding the bulk oil circuit breaker. In a bulk oil circuit breaker, we have used oil as the insulating medium and also as the arc quenching medium. But to serve the purpose of both arc quenching and insulation, we have needed a huge quantity of oil, normally above 50 kiloliters of oil. A bulk oil circuit breaker with a 31.5 kiloampere short circuit breaking capacity requires more than 50 kiloliters of oil, and during an arc, the oil decomposes. The oil decomposes to produce hydrogen gas, and this decomposition also produces carbon particles. This means that due to repetitive arcing, the repetitive short-circuit operations degrade the quality of the oil due to carbonization. As a result, after a certain specified number of faulty operations or operations during a fault, we need to replace the oil. As the oil generally gets degraded after a certain number of faulty operations, this replacement requires a huge quantity. This replacement consumes a huge quantity of new, fresh oil, which is not economical. Also, a bulk oil circuit breaker occupies a large space. The erection of a bulk oil circuit breaker is also challenging because of its huge size and weight, and it also occupies a large space. To minimize these difficulties, engineers developed the minimum oil circuit breaker, where arc quenching happens only inside the oil-filled enclosure and the arc interruption mechanism. A compartment contains the entire current interrupting mechanism, and it stays live, and this portion of the circuit breaker is an insulated column supports this arc quenching current interrupting chamber. So this circuit breaker will have two parts: the arc quenching current interruption chamber, which is the upper part of the circuit breaker, and the supporting insulator, which is the lower part of the circuit breaker. There is another compartment attached above the arc quenching chamber, and we refer to it as the top chamber. This top chamber provides the space above the oil level to accommodate the gases formed during the arcing phenomenon. This top chamber also contains an oil level indicator, and just below the top chamber, there is a terminal, which we also refer to as the top terminal of the circuit breaker. That terminal connects to the external circuit and the bottom of the arc chamber. There is another terminal, and that bottom terminal connects the other part of the circuit. So there are three chambers. One is the top chamber, which provides the required vacant space above the oil for accumulating decomposed gas during the arc. The middle chamber, which we sometimes also refer to in general as the top chamber, contains the current interruption mechanism, and the third chamber is normally a hollow cylinder of porcelain insulator that also contains oil. We also fill that chamber with oil. But this oil does not have any direct relation with the oil of the arcing chamber. It is separated and filled, and we refer to the entire assembly of the top chamber, middle chamber, and bottom insulated chamber as the pole of the circuit breaker. In a three-phase circuit breaker, there are three such poles, one for the red phase, this is for the yellow phase, and another for the blue phase. And then these three poles are placed on the circuit breaker base. The base of the circuit breaker contains the tripod and lever assembly to facilitate the movement of the moving contact during the closing and opening operations of the circuit breaker. This is the local mechanism. This is the mechanism box, which contains the spring charging motor and other lever gear assembly to operate the circuit breaker. It also contains the auxiliary circuit, as well as anti-pumping relay, DC failure relay, and auxiliary AC circuit for door lights and heaters, etc. This is the basic structure of the minimum oil circuit breaker. Now we come to the working principle of the circuit breaker. This is the moving contact. This is the fixed contact. These two parts are also moving slightly downward. The gas pressure generated during the arc mainly causes this movement. We will indicate the gas later. Now, observe how both portions move down. The spring compresses during this motion. Under normal closing conditions, this part touches the fixed contact. It blocks the gas exhaust vent path. Now suppose the contacts are opening. The moving contact moves downward. At this time, current is flowing in the circuit. This means the breaker is interrupting a live circuit. So, arcs form between the contacts. I will not explain the reason here, as I assume you already know why arcs occur when a breaker opens a live circuit. The entire contact arrangement is immersed in oil. Although the oil is transparent, it is not shown in the animation. Assume that everything is happening in oil, meaning the contacts are opening inside it. The arc temperature here will be well above 1000 degrees Celsius. This intense heat vaporizes and decomposes the surrounding oil. Since oil is a hydrocarbon, decomposition produces hydrogen. As a result, a bubble of vaporized gas and hydrogen forms around the arc. As the arc continues, the bubble grows in size. The increasing hydrogen gas serves two purposes. First, it raises the internal gas pressure. Second, it forces the hydrogen to exhaust through the upper vent. This creates a flow of hydrogen gas. Hydrogen has a very high cooling effect and excellent deionization capability. Due to the combined cooling and deionizing action of the hydrogen flowing along the arc axis, the arc is quenched. Since the gas flows along the arc axis, this type of breaker is called an axial flow. MOCB, minimum oil circuit breaker. After arc quenching, the gas escapes through the vents. At the current's zero crossing, the arc naturally extinguishes. With no arc, no further heat is produced, so the oil no longer generates gas. The remaining gas from the previous current cycle quickly passes through the vent and fresh cold oil flows in to take its place. As the moving contacts travel further downward after arc extinction, the lower oil vent opens. This provides a cleared path for the oil to flow upward and fill the gap between the contacts, restoring dielectric strength. The high dielectric strength of this fresh oil prevents arc restriking, ensuring the current is fully interrupted. The previous one we had seen was an axial venting minimum oil circuit breaker. Here hydrogen gas flows axially along the axis of the arm. There is another type of venting available for minimum oil circuit breaker. That is cross-venting or radial venting. The constructional details are the same as in the axial venting. The only difference is its working principle and the direction of venting. This is the cross-section of the insulator housing. This is the wall of the arc interruption chamber. These are the paths for entering the oil between the contact gap. These are the paths through which the gas exhausts during arc quenching. This is the moving contact. This is the fixed contact. During opening operation, the moving contact moves backward. Therefore, the arc starts between the fixed contact and the moving contact. As the moving contact goes away from the fixed contact, the arc length increases. Thus, the quantity of hydrogen gas produced by the arc also increases. As a result, the size of the bubble increases while the moving contact moves backward. When the vent openings uncover, these vents open one by one. The arc and the gas then get a path to exhaust. At the same time, fresh oil comes in. It occupies the vacant place through this path and fills the gap between the moving and fixed contacts. This fresh oil then pushes the gas outward through the vents. Ultimately, the gas bubbles rise upward through the bus and accumulate in the vacant space at the top chamber. The advantage of the minimum oil circuit breaker is that it requires a very small amount of oil. It requires around 10% of the oil, compared to that of the bulk oil circuit breaker. As a result, the weight, size, or volume of the circuit breaker becomes much smaller than that of the bulk oil circuit breaker. Due to the lesser quantity of oil, these circuit breakers suffer less from fire hazards. However, there are still some disadvantages to the minimum oil circuit breaker, which we also call small oil circuit breakers. First, carbonization also occurs due to the decomposition of the oil during an arc in the minimum oil circuit breaker. Therefore, replacement of the oil after certain faulty operations is also required in the minimum oil circuit breaker. Although this replacement is much easier than that of the bulk oil circuit breaker, because of the lesser quantity of oil to be replaced, the quantity of oil is less here, but it still suffers from fire hazards. However, the chance of fire hazard is lesser than that of the bulk oil circuit breaker. After the development of vacuum circuit breakers and SF6 circuit breakers, nowadays both bulk oil and minimum oil circuit breakers have become obsolete compared to modern circuit breakers. I hope you got the basic idea. Thank you.
If you found this helpful, don't forget to subscribe, like, and tap the notification bell. Got questions or want us to cover a specific topic? Leave a comment. Thank you.